Yesterday you had an intro to imaginary numbers. You were told that the square root of -1 is equal to I, and I is our imaginary number. You looked at the rotation on the complex plane. So the horizontal axis is your real axis, the vertical is your imaginary. This right here, when you're just going one out on the positive real axis, is just 1. Now if you rotate that, so think of this in terms almost of a vector. If you rotate that 90 degrees, this is I. If you rotate that another 90 degrees, that's going to be -1. And when you rotate it another 90 degrees, this was your -I, and then you rotate another 90 degrees, you're back at 1. So seeing this here, you rotate that one time, that's your I to the first power, and that's I. You rotate it twice, that's I squared, and it landed on -1. You rotated it 3 times, you were at -I, and then you rotate it again at the 4 times, you're back where you started, and you're at the real number 1. Okay? So we're going to look at today is evaluating I to some higher powers, not just 1 through 8. So if we look at I to the, we'll start a little small, I to the 7th power, that means that you're rotating 7 times around the origin, 90 degrees. So you start here, so here's 190 degrees, 2, 3, 4, and then you keep going, 5, 6, 7. So based on those 7 90-degree rotations, this is going to be equivalent to a -I. Now we don't always want to have to go through the rotations, especially as the numbers get big. So we can do a few things. You can look at this in terms of I times I 7 times. Okay, this right here is your I to the 4th, which we know is 1 because that brings us back to the start. This is your I cubed, and we see up there that I cubed equals a -I, and we get to a final answer of -I. So you can go that route too. Because you're always rotating 90 degrees, every revolution, every circle is going to have 4 90-degree rotations. So another way you can look at this is think about this as if you're doing 7 divided by 4 goes in 1 time with a remainder of 3. So what that's telling you, if you were to rotate that starting number, that starting vector 7 times, you're going to have 1 full rotation, and you're left over with 3 90-degree rotations. So where are you left over when you're looking at 3 90-degree rotations? At -I. So this approach is going to be a little bit easier when you're dealing with some larger exponents. So let's go ahead and look at number 2. If we're looking at I to the 21st, you might think about how many full rotations are you going to do? Obviously, we don't want to have to start by counting 1, 2, 3, 4, and so forth all the way to 21. You can do 21 divided by 4. And you're going to have 5 full rotations with a remainder of 1 90-degree rotation. So I to the 21st is going to be equivalent to I to the 1st power. And what is I to the 1st power? Just I. So if we were to try I raised to the 46th power, again, we don't want to have to go through and do 46 rotations, so let's think about how many full rotations are we going to have. So if we do 46 divided by 4, it's going to go in 11 times with a remainder of 2. So what is that telling us? That means if you were to take this vector, okay, or that number, however you want to think about it, and rotate it 11 full rotations around and around and around and around and around, and then once you do that 11 times, you have 2 90-degree rotations, and this is where that number is. And where is that? That's at your I squared. And what does I squared equal? -1. Now the next thing we're going to look at for today is looking at what's called the absolute value or the modulus. That's also known as the modulus of the absolute or of the complex number. Okay, and this is pretty easy. All it is asking you to do is find the distance away from the origin. So if we take a look at the number, you graphed this one yesterday in class, I think, 2 minus 5i. So if you look at this, this is telling you that you're going 2 in the reals and -5 in the imaginary. Okay, and we're just trying to find that distance. How far away is that number from the origin? That's what it means to take the absolute value of a complex number. So it might just say find the absolute value. It may have the absolute value around it. But what you're trying to do is just, what is that distance? If you could take a tape measure and measure that, what is that distance? The easiest thing to do and think about here is if you were to draw this up, you would have a right triangle, right? And how do we find our hypotenuse? It's your Pythagorean theorem. So we would do 2 squared plus 5 squared equals that distance squared. I'll just call it c squared. And to solve for c, it's the square root of that. So we get 4 plus 25, and the distance that that number is away from the center is the square root of 29. Okay, so you can think about it just in terms of Pythagorean theorem, or you can just think about it if the number is a plus bi, the absolute value of that, the modulus of that, is just the square root of a squared plus b squared. So this is your formula that you're going to take away from this. Okay, we'll do one more of these, and then that'll be it. So number 5, if we wanted the absolute value of -3 plus 4i. So let's just practice graphing it, just so you can see it. You don't have to do it to answer this, but just for practice from yesterday. This means we're going -3 in the reals and then +4 in the imaginary, so it's right here. And so what you're looking for is this distance right here. How far away is that point from the origin? Again, you can draw the right triangle, or if you just follow the formula there, the absolute value of a complex number is just the square root of the a squared plus the b squared. And you don't even need to include the negative, right? Because a -3 squared is a +9. So we get 9 plus 16, and it's the square root of 25, which is 5. Okay, so you guys are all set for the next day. Go ahead and complete that worksheet. It shouldn't take you too long, and I will see you tomorrow.